going to be received, but over the years now we've built a good audience, and love it if you bring more of your friends with you. The lecture series is named after Starling Trimble, who was the father of the astrophysicist Virginia Trimble. And when her father passed, Virginia made a donation that made it possible to continue the lecture series and formalize it as it is now. So tonight we're having our third lecture of the year. Our fourth lecture of the year is indicated on the first Wednesday of November on the backside of your card on the table. Sarah Schechner from the Scientific Instrument Collection at Harvard will be giving a talk on objects in American astronomy. And this is a topic that won her the award of the History of Astronomy Division at the American Astronomical Society. It's an interesting piece of work, and she's a good storyteller. So come again 1 month from tonight, and you'll have another chance to hear a Trimble lecture. We have a number of talks that are, well, we have 3 talks that are lined up and scheduled for next year, and a fourth one that we're just working on the date. So by the time of the November Trimble lecture, I'll be able to fill you in on all the specifics. There's no sense giving you a work in progress report on that. So let me now introduce Fred Villa, who was the Chief Executive Officer of AIP until a few years ago when he retired. He's back out of retirement to introduce tonight's speaker, and I think as he introduces her, you will find out why she's doing it.
Thank you, Greg. It's good to be back in this building. It's been very familiar faces with friends and colleagues. I spent about 12 years working with various kinds of organizations. And it's probably no secret to my friends at the Center for Physics and the Universal Archive that I love what this organization and our members societies do for history and preserving the history of what physical sciences have done to the country and the world. Now, the reason I volunteered to introduce the speaker is that I've had the pleasure of knowing Catherine for about 30 years, since we were both teenagers. You are honored to have another historian who has been the historian of 5 Department of Energy National Laboratories. Fermilab, Argonne, Berkeley, Los Alamos, and Jefferson. I think I got all 5.
Yep, you got all 5.
Prior to my exercise here at the American Institute of Physics, I worked at Jefferson Lab. And Catherine was the historian of record, putting together the history of the department's newest national laboratory. Before that, it was Fermilab. So she is on record as recording the history of the 2 newest national laboratories. And I remind you that the Department of Energy is the largest funder of the physics science in the country. Of course, the national lab is many of you know. And our course is usually Manhattan building. You're going to hear a fascinating story, Catherine, about how the National Labs, after their initial focus on supporting weapons complex, they were run by particle physicists, well-known particle physicists. They smart, and they ruled the roost of physics and physics funding for many years, particularly in the National Lab complex, for larger and larger accelerators. But one of the reasons accelerators got larger, other than the boost the energy for different higher energy particles, was a waste product of accelerating particles. It's called X-rays. And if you made the accelerators bigger, you could spread out that radiation. And fortunately, you'll hear from Catherine tonight, there was some very clever material which say, this is exactly a waste product. If we just put a little window on what the X-ray is out, it would be the brightest source of X-rays that we have, this matter. And so Catherine will tell us the story of the big change of how big science went from particle physics to material science. And I've had 33 years of it, and my experience is too quite laboratories. It's a fascinating thing to go through, and I'm sure you're going to enjoy the next lesson. Catherine, the floor is yours.
Thank you. Thank you for the excellent introduction. Now, part of what I was going to say at the very beginning, I definitely say, indeed, I am chronicling what my newest passion is, to chronicle this new era in the national labs, the largest projects at the national labs, which are for material science instead of, as in the past, in particle physics. The term the new big science is something that I've come up with collaborators, and we are writing a book on the subject. And today in particular, I am going to spend quite a bit of time in talking about how the transition was made between big science and the new big science, and then a bit about what difference that transition made. In the beginning, of course, there was big science. Big science is a term that was coined by Alvin Weinberg and Derek de Sola Price in the 1960s. And the definition was that in big science, everything is getting bigger. The tools get bigger, and the teams get bigger, and the price tags get bigger. And in particular, they were talking about accelerators and reactors. But as time went on, it got to be more and more about accelerators, in fact, and accelerators for particle physics, which, as Fred mentioned, had to go larger and larger, had to be made larger and larger in order to investigate smaller and smaller subatomic realms. Interestingly enough, originally de Sola Price and Alvin Weinberger considered big science to be bad science. It was big, bad science. It was a disease. However, eventually, particle physicists, which, as Fred noted, are not exactly dumb, came up with the idea of turning big bad science on its head and saying, yes, our science is big, which means it's better, it's grander, it's more worthwhile than other forms of science. So big science becomes a justification for getting ever bigger for particle physics. But in addition to that, it wasn't just that. It also becomes the justification for building and maintaining the national laboratory systems in the first decades after World War II, because of course the rationale for building these large accelerators that become the justification for these labs is that they are tools too big for universities to build. Just briefly, I will point out to two of the biggest discoveries that made big splashes. There is on the left here the antibioti, which was discovered at Berkeley in the 50s, and then on the right there is the J-side particle, which provided compelling evidence for the existence of quarks, which and in turn was a key step, its discovery was a key step in the development of particle physics standard model. So big science is about getting bigger, And through the 50s, then the 60s, and into the 70s, there is this succession of large particle physics machines with a plan for the next big thing being Isabel. One of the things to notice as we go along is that particle physics accelerators, as they get bigger and bigger, fewer and fewer of them can be built because of expense for one thing. But the other problem is that, or the other issue that had to be dealt with, is that even the community that would use them is limited. So there were, over time, fewer and fewer of these big machines. But I'm here to tell you a big secret, and that is the big science era was not just about particle physics. All along, these multidisciplinary labs nourished a large number of different kinds of projects. What happened? For example, at Lawrence Berkeley Lab, there was, in the mid-70s, there was the Nuclear Science Division, the Biomedical Division, the Energy and Environment Division, and the Inorganic and Materials Research Division, which will come up many times as we go on. So at the national labs, there are these small and medium-sized accelerators, as well as an abundance of state-of-the-art smaller devices. It wasn't just about the great big particle physics machine. And in fact, starting in the 60s, we have the development of what I think of the roots of material science, this interdisciplinary, multidisciplinary field that begins to grow. And at the small scale, it is developing at universities and industrial labs. At what I think of in the intermediate scale, they have these government-sponsored material research laboratories that brings together universities and industries to work on common multidisciplinary projects. And then Berkeley has an Inorganic Materials Research Division again, and to give another example, Argonne has its Solid State Science Research Division. So these projects are flexible, multidisciplinary, and interdisciplinary. They are multidisciplinary because they bring in people with specialties from engineering, chemistry, physics to work in an interdisciplinary way on common projects. And in the process, they use skills and methods from the various fields that bring the specialists together. And in physics, because I know there are quite a few people who are interested in the history of physics in this room, in particular, during this period, you have this great expansion of what is first called solid state physics and then eventually gets to be called condensed matter physics. And I can't mention that without giving a plug to Joe Martin's wonderful book, The Solid State Insurrection, which very carefully chronicles that very transition. Now, from these roots in material science, we begin to have infrastructure sprouts, and I will talk a little bit about the types of machines that develop. There are two categories. There are neutron sources and light sources. And light sources is what Fred was talking about. In addition to that, we have reactors, research reactors, and pulse sources. Now I go from, in a historical way, in terms of the way in which they were, the times in which they were developed. The two oldest research reactors in the U.S. National Lab context were at Brookhaven and Oak Ridge. And conceptually, this is very simple. You create collisions, neutrons are produced, and they're conveyed into an experimental area, and they hit something, and they create measurements. Synchrotron light source, this is what Fred was talking about. At a synchrotron facility, electrons are usually accelerated in a synchrotron and then injected into a storage ring, and we'll hear more about storage rings. And there they circulate, producing synchrotron radiation. What originally was thought to be garbage and then came to be seen as something that was scientifically useful. But they don't gain further energy. The radiation is projected at a tangent to the electron storage ring and captured by beam lines. At Argonne, they developed, and subsequently has been built elsewhere, the first pulse source, the intense pulse neutron source. In such a system, ions are created in a hydrogen plasma, further accelerated in pre-accelerators, then passed through bending and focusing magnets and injected into a synchrotron, stripped of electrons to produce a pulsed proton beam. This pulsed beam is then carried through a beam line to a target, in this case depleted uranium, to produce short pulses of fast neutron by spallation. Spallation is what happens when particles in a beam hit a heavy target and produce numerous light particles, mostly fast neutrons like chips hitting from a stone hit with a spalling hammer. Moderators around the target slow down the fast neutron to the desired energy, and the resulting neutrons are directed to beam holes which are equipped with measuring devices. Here is a full list of neutron sources in this period before 1980. And in addition to the ones I've already mentioned, we have the Chicago Pile series at Argonne. They date it, interestingly enough, from CP1, which was the original reactor that Fermi used to show that you could create a self-sustaining chain reaction that allowed the development of the bombs in World War II. And they continued that series up through CP5, which was a research reactor. Let's turn to light sources. There was a first generation that ran parasitically. These were as a kind of side product to particle physics accelerators. When they had extra time, they would allow material scientists to come in and use them, for example, at SLAC, at the Stanford Synchrotron Radiation Light Source in the 70s. Eventually, you have the second generation light sources, which are built for the purpose of doing material science. The first big one was at the National Synchrotron Light Source at Brookhaven, and Aladdin at the University of Wisconsin, which built on the technology of the Tannis storage ring from 1968. So these early machines had a variety of applications. There was fundamental physics, looking at the structure and properties of atomic and subatomic matter, and then investigation of materials. Particularly important were the materials that you would want to use as you developed better and better reactors for civilian nuclear power, and also the production of radioisotopes. Interestingly enough, biomedical applications were important very early. So through the 80s, you have this growing community of users. You do have users. It was interesting for me to see that at the national laboratories, these projects often are instigated by accelerator experts. And what's happening is, at the national laboratories, you have these accelerator experts who build accelerators for particle physics, but then there aren't very many of the, as time goes on, fewer and fewer, they're getting larger and larger and fewer of them being built. And so they come up with ideas for alternate accelerators, including material science accelerators. Around 1980, a change was happening. I think of it as the twilight of the big science era. The two big projects are still, on the left we have Fermilab, on the right we have the Stanford Linear Accelerator. The biggest projects are still at Fermilab and SLAC, but these were single-purpose laboratories. They no longer were used to justify the existence of these big labs. And then the idea is they would be superseded by the newest big thing. Isabel was canceled, and so it was the ill-fated superconducting supercollider. And I show this just to give a kind of flow of how these various events in the National Laboratory are happening, and I'll go through them one by one. Berkeley lost the machine that was built at Fermilab and has something called the Bevilac, and this is a relatively small accelerator called the HiLac that accelerated heavy ions, and those heavy ions are conducted by a beamline to be circulated at relativistic energies in the Bevitron, which had outlived its usefulness as a particle physics machine. So we have the start of heavy ion nuclear physics. Because Isabel, as I mentioned, was canceled at Brookhaven, this partially built tunnel is used for another nuclear physics project called the Relativistic Heavy Ion Collider. And what's happening at Oak Ridge and Brookhaven, they're hanging on to their reactors from the 1960s. We do have the intense pulse neutron source that was developed in the 70s, but by the 80s it's already struggling. It asked for an upgrade and it got denied, and the French reactor ILL took over as the machine that has the greatest neutron flux, and ISIS in Britain becomes the most important pulse source. In addition, the second generation light sources are struggling because for technical reasons. So to give a kind of recap to this overall history, new projects are for nuclear physics, mostly using recycled particle physics equipment. An exception is JLab, where Fred and I worked, which was being built in the early 80s as a nuclear physics facility for electronuclear physics. But that left 3 labs that are in great needs of projects to justify their existence: Berkeley, Argonne, and Oak Ridge. And this very large superconducting supercollider that's taking a lot of the oxygen out of the air. So enter David Shirley. He becomes director of Berkeley Lab in 1980. He was jointly appointed in the esteemed chemistry department at UC Berkeley, and when he was appointed, he had a joint appointment at the Inorganic Materials Research Division, which I've mentioned a couple of times, and he had worked at SSRL parasitically at SLAC. So he has an idea. Why not justify Berkeley's existence? I mean, that's the purpose of a laboratory director, sort of on a basic level, is to keep the laboratory open. And so he has to justify Berkeley's existence. So he comes up with the idea of a third generation light, doing so with a third generation light source. In this case, he had the idea for a 2 GeV light source. And a third generation light source is optimized with beam insertions so that the light is brighter and more controlled. And thus, what came to be called the advanced light source emerged. And this was the first time that a multidisciplinary lab was justified with a material science project. The time seemed ripe to him. Berkeley had lots of accelerator expertise, and in fact, in the great group, expert group of accelerator builders, there came an idea for a new undulator, and there was the whole issue of needing to survive. So Shirley does what previous Berkeley laboratory directors do. He goes to the top and makes a deal. In this case, goes to a top administrator in Washington and makes a deal. In this case, it's with Jay Keyworth, who at the time was the presidential science advisor. And then in due course, in 1981 and 1982, the Berkeley group creates a proposal and has a very successful Department of Energy review. And then everything goes wrong for poor David Shirley and LBL. As the funding for the advanced light source is going through Congress, there is just a huge storm of protest. There's a letter writing campaign. And people point out that the second generation light sources are struggling. And part of the problem, sadly, was Shirley himself. People who liked Shirley saw him as a man with vision, which I agree he had, but he also was very edgy. He was a hard-charging. He wasn't diplomatic at all. He didn't understand that life had changed when the Atomic Energy Commission merged into the Department of Energy and was a much more bureaucratic institution than that. He needed to develop relationships within the material science community and also within the funding agency. But an important thing to realize is that it wasn't just that Shirley screwed up. It's also the very nature of the material science community, and this will come up again, is that it's not like the particle physics community. In order for particle physics to evolve, you need a bigger accelerator, and everybody wants that next bigger accelerator because that's the way to advance the field. And that's just not the way it was, and not the way it still is in material science. It's not that a material science accelerator can't give you some exciting new possibilities for advancing your research, but it will never be the only way or the best way necessarily to solve a material science project. Luckily for Shirley, at just this point, there was something in DOE called Basic Energy Sciences, which had only been founded a few years before, and it was headed by a great guy named Louis Ionello. And in fact, Shirley, in his brusque way, had sort of treated Ionello like he was supposed to just carry the water that Jay Keyworth and he had given him to produce the advanced light source. And Lou Ionello later told me, yes, that was irritating, but he also saw that there was something here that was very useful. Very useful for basic energy sciences, very useful for Lawrence Berkeley Lab, and very useful for science. This idea of developing a material science accelerator to justify the existence of a laboratory. So Aianella did what administrators do when they find themselves in this situation, and he decided to see that a number of committees were convened. And the basic idea was to get scientists who might use material science accelerators, but really the Berkeley's advanced light source together and get the consensus to build the Berkeley machine. And there were many more than this, but I have mentioned two of the big ones here. In 1983, Peter Eisenberg and Michael Notek had a committee that looked at life source priorities. And in one of those funny little things that happens in history, the people that were there to talk about how exciting it would be to have a 2 GeV light source decided that actually it'd be much more interesting to develop a 6 GeV light source, even though the criticism for the 2 GeV light source was that the other second generation light sources were struggling and it was too big a step, but somehow they got very excited about a 6 GeV light source, which came to be called the advanced photon source because it was capable actually to get bright enough light that you could do imaging. Michael Notek subsequently told me the advanced light source forced the light source community to come together and think about a shared future for the first time. So this was a very important moment for that community of users to grow and to gain excitement, first about using light sources and then eventually the other types of material science machine. So that in 1984, Frederick Seitz and Dean Eastman had a committee that looked at the large-scale material science facilities, which included the neutron machines as well. So I date the dawn of the new big science from the mid-1980s. And it was at this time, there were lots of projects, and that was part of the problem that was developing. And I mentioned the three laboratories that needed projects in order to justify their existence. In addition to Berkeley, Argonne latched on to the 6 GeV advanced photon source, and Oak Ridge latched on to the idea of an advanced neutron source, which was a reactor, eventually largely because of the anti-nuclear movement, they switched so that they were championing an upgraded spallation neutron source. So in addition to those three projects, for nuclear physics, we have the heavy ion collider at Brookhaven and what became J-Lab in Virginia, and of course, this SSC. So Alvin Trivelpiece, he was the director of the Office of Energy Research in 1981 to 1987, and he was the one who was in charge of nurturing these projects and nurturing the basic research, the research that was being done at all the national laboratories. And I remember I caught up with him at an APS meeting, and I remember him talking about those days, and he said that it was really, really starting to concern him because all these laboratory directors were worried about the existence of their either their up-and-coming projects or these new projects that they wanted to get, and they were trash-talking each other, and they were pushing really, really hard for funding. It was a kind of toxic competitive environment. And so he began to worry that it was even going to threaten the SSC, which was also starting to get some criticism because it was so expensive. So he said, okay, this is what we're going to do. We're going to come up with a gentleman's agreement, and you're all going to say, none of you are going to criticize each other's projects, and most important, no one is to criticize the SSC, which many felt was needed to support the national laboratory system as a whole. And instead, everybody gets something. Berkeley will get the advanced light source, Argonne will get the advanced photon source, and Oak Ridge will get something later, the spallation neutron source. Brookhaven will get RIC, and there will continued support for what became JLab. And then, to everyone's horror, at least at DOE and in the particle physics community, the SSC was canceled in 1993. I have come to believe that it basically was a victim of weak leadership, that is, that there weren't the leaders that could make the kind of connections and build support within the scientific community, or to win political support. And in addition, there were management woes and Waxahachie, there was inefficiency and sharply increasing costs, and of course, the management woes made the weak leadership, made it harder to have leadership, for the leadership to be effective, and vice versa. But I kind of think that although the end of the Cold War didn't help, I become convinced that the right people probably could have averted cancellation in 1993. But that kind of misses the point, because particle physics depended on this unsustainable dynamic of growth. And if it hadn't been the SSC, it would have been the next big project. After that, when I look at the numbers, it wasn't even clear to me that there were enough particle physicists to build and use the machine. And when I told that to Michigan State particle physicists at the time, this was when I was pregnant with my now 28-year-old, in 1990, and he was, poor guy, was frantically advocating for the SSC. He told me, you have to understand, particle physicists go to higher energy. That's what we do. We'll go to higher energy until we die. And the bubble over my head was saying, so in other words, you realize you're going to die. So I think that eventually the new big science would have emerged, in part because there was this developing notion already that these laboratories needed projects to justify their existence. It wasn't going to be a succession of particle physics accelerators, and the material science, the ingredients were there for particle physicists to have projects and a growing community of people who were interested in using them. And unlike particle physics, because of the nature of particle physics as a discipline, it has sustainable growth. So the new big science emerges by default in 1995, the largest with the SSC no longer, as the SSC is being dismantled, the part that was built, the largest DOE project is Argonne's advanced photon source. In 2006, it became Oak Ridge's spallation neutron source. And in 2002 to 2009, SLAC changed its mission from particle physics to material science. It does a variety of things, but its main mission is material science. And it rebuilt the sphere storage ring and repurposed the original LINAC to build the LINAC coherent light source in FEL. And if you want to know about that, ask Fred. He's Mr. FEL. So I've talked a lot about process, and I didn't want to leave you with the idea that these big accelerators are just built for no really exciting good reason. So what I did was I went to the websites of the biggest machines, and I just picked something that looked particularly interesting to me, and I encourage you, if any of these particular projects look interesting, or if you just want to see the projects that might interest you, to look at the websites yourself. This particular one comes from Argonne's Advanced Photon Source. It's a soil bacterium. It's glowing here brightly under ultraviolet light. It exudes an antibiotic that has a novel structure that hopefully can lead to a new antibiotic. This comes from the Oak Ridge machine. It's an artistic rendition of the intriguing superionic crystalline structure, which has copper ions that move like liquid between solid layers of chromium and selenium, giving rise to useful electrical properties. And these people come from SLAC, and they have discovered a practical starting point for converting carbon dioxide into sustainable liquid fuels, which promise to be important for heavier modes of transportation that are hard to electrify, such as airplanes, ships, and freight trains. So, to give a little snapshot of the difference between the old particle physics versus the new big science, material science. The largest projects are for material science. The ones that are used to justify the largest labs are for material science, not particle physics. They have practical applications. They have many government industrial partnerships. They're diverse in content and user base, and I'll speak more about this later. And the use of the instrument is goal-oriented. In other words, the users come in to make a particular measurement for a particular purpose, but the users fluctuate. And one thing that I've noticed that was really interesting, and one of the many things I had to learn about working with people who use these machines as opposed to particle physics or nuclear physics machines, is that I actually haven't met one yet who identified as a material scientist. They tend to identify as engineers or physicists or chemists who do material science. So it's neither a coherent or stable group, but it has sustainable growth. And another thing about it, it's very international. I mean, the number of light sources, there are light sources everywhere. It's not just Europe and the United States or even North America. They're in the Middle East. They're all over the place. As in the old big science era, the new big science has a variety of projects. There are the nuclear physics projects that I've already mentioned, and also there's still one particle physics lab, Fermilab. So let's go through a little more in detail about how science is done at material science accelerators. It's the integration of the industrial presence from the beginning. There's the scope and complexity of the networks, so that if we think about an individual beamline, you have people who come to work on that from a wide variety of different industries, from a national labs, from maybe a hospital. And not only that, but the people are connected to, since they are working on applied projects, they're connected to people who are preparing the technologies and ushering them into the marketplace. There's the octopoidal, octopus-like character of research networks. So not only do you have this complexity of the individual beamlines, but the beamlines very quickly proliferate. You have what we call the multi-stability of techniques, and this is something that I'm interested in learning much more about. But you have this creative process where you have researchers that come from very different fields who are making measurements for very different reasons with very different specialties. And so they come up with a lot of different ways of doing scientists, and they share techniques. They borrow from each other's toolkits, so to speak. In addition, you have the proliferation of sub-facilities that material scientists will use not only these big machines, maybe more than one, but they also use desktop facilities, all different kinds of facilities. And there's something that's called the Krinsky effect that was named after Sam Krinsky at Brookhaven, who remarked about how remarkably patient material scientists are compared with particle physicists. And again, this has to do with the fact that they don't depend so strongly on a particular device in order to do their work, and therefore it's the same. Another consequence is that sustainable growth. In the time, and I've talked about this a lot, as you go, starting in with the advent of the Department of Energy and to the current day, there's been more and more regulation anyway. And if you put industrial partners and medical partners into the mix, that regulation only gets more and more. A little bit about the formation of knowledge, just to point out that whereas in a particle physics accelerator, you have individuals all getting pieces of the same puzzle that they put together. In these machines, you have individuals coming in and getting pieces of a grand variety of puzzles that are being put together. This leads to all kinds of intellectual property issues. There's the issue of timely access. And it also, you might think that because of the practical applications, it would be easy to make the political and scientific case, but the very complexity of it makes it hard to talk about, because it's hard to even think about it. And so selling it as to why you need the advanced photon source or the spallation neutron source, when they're only used to give a piece of all these different puzzles, can be very complicated. On the other hand, there are these huge advantages. There are all these promises of applications. There are a large constituency of potential users. And again, to say one more time, the growth is sustainable. One thing I wanted to say in passing, and this is something that I thought of as I was doing this very presentation, is that in big science, we have particle physics is the biggest, material science is the smallest, and nuclear physics is in between. In the new big science, particle physics and material science switch places, but nuclear physics is still in the middle. So the question in my mind is, as we evolve from the new big physics, will particle physics go the way will nuclear physics go the way of particle physics, or will it remain sustainable like material science? No idea. So the new big science has challenges for historians, just again that complexity, the same thing that makes it harder to justify politically and to make the scientific case. I was particularly confounded when I first started, because I always like to follow the money. Following the money in these projects is almost impossible. They get funding from a grand variety of sources. Unlike particle physics or even nuclear physics that get almost all of its funding from one part of DOE or maybe NSF, the funding comes from all kinds of industries, from NIH, DOE, NSF. Following the money is very difficult indeed. And even following how the applications evolve from the puzzle pieces gathered from these devices is difficult. So investigating the new big science is a challenge, but it's worthwhile. And I'll leave you there. Thank you.
Okay, thank you very much, Catherine. Time for questions. Okay, first Will and Alan, and then we'll come to Mike, and I won't try to remember more than that.
Greg, you want Wendy to run around?
That would be great. Could you do that, Wendy? Okay, thanks. I might fall over.
Thanks very much, Catherine. That was great. You're really speaking my language as both a historian and a policy analyst. I've looked at a lot of these DOE facilities, and they're current. Sorry, did somebody? You're okay. All right, in kind of the current politics surrounding them, and one of the things I'm wondering if you.
Well, it sounds like I need to talk to you. I would say that having these large material science projects justify the existence of these multidisciplinary labs was very difficult at first for science administrators. And I know that they struggled in order to make I was around even in the early 2000s when Pat Damer was saying, no, we're not going to have these cats be allowed to industrial sources fund these beamlines because then DOE's not in control. And this caused a great deal of consternation because it seemed like it was a good idea to bring in industrial bucks into these large facilities. And Damer's point was, yeah, but we're spending all this money to maintain these devices, so we need to be able to have control and not to give that control over to industries who just give a relatively small amount. I also went to user groups where there was a great deal of incoherence as users who were all interested in using a beamline, and they might all be advocating for a particular beamline, but they literally didn't speak the same language. I mean, you have medical doctors and engineers and you know, it was a military project. There were physicists, there were chemists. And so you need some way. One of the problems that I saw through the mid-2000s was the need to have advocacy groups to advocate for particular topics in the science itself. So it sounds like that's what they did. It sounds like they developed these interest groups who could advocate for the science. The other thing I would say that I always wondered is that part of the way that these big machines were, a question that's still in my mind, I still haven't figured out, was that in particle physics accelerators, you can talk about Nobel Prizes and that sort of thing. And they try, but you know, the applications that come out are not strictly traceable back. It's really hard to say without this $2 billion SNS, we couldn't have had this application. So sounds like we need to talk more in the future.
Most definitely, thank you.
Right here. Wendy, closer up this way. Raise your hand.
Thank you, Catherine. Extremely interesting presentation from the inside. And what struck me is I've also read the same story told by Philip Morosky from a much different Science Mart, where he's very much more critical. And obviously, it's very much the same timing, 1980s, as the great transition in neoliberal market values rather than intellectual scientific values. And I wonder if you have any inclination to try to integrate the critical perspective with the internal perspective that you outlined here.
Well, what I am clear about is that something happened in 1980. A colleague referred me to a article by our friend Paul Foreman, who talks about 1980 being the demarcation in postmodern, which I actually haven't read. So clearly something, and then my Swedish collaborator, Thomas Kaiserfeld, has come across some readings about also 1980 being a crucial point.
We should look at Science Mart, Philip Morosky from
Thank you.
Hi, thanks for that talk, very interesting. I wanted to ask you a question with a little bit different tack. I know there's always a creative tension between the big science projects like you've described and the smaller research groups. And it's interesting that it seemed that demarcation between the very large science where everyone was focused on one project or one result has changed into this idea of a national facility which then supports numerous smaller endeavors. But in the same way, in many cases, the big science you talked about where things changed in the 80s, papers became incredibly long just on the author list.
Right.
And so, individuals or individual groups didn't have a mechanism to have credit or in a way credit given for their research. So I'm wondering if you comment on kind of that dual thing, which is the tension between smaller groups and smaller projects versus the big science and the money going for that and then not available for the smaller groups, but also then for just that idea of credit. How do you get credit in the old big science model?
Well, that was one of the problems with the old, well, which still exists, by the way. I mean, particle physics still exists, and they still have these giant collaborations. And in fact, the largest nuclear physics collaborations that I talked about are pretty darn big, and have this same kind of projects. I remember again something that Lou Ianello told me. The guy who was at the beginning in BES, and he said that, which gets, I think, to this, that the thing about particle physicists, he said he would go into a room of particle physicists and it was like talking to one person. So there might be a lot of them, but they all bought very strictly into a particular value system and a particular pecking order. Even the ones who were at the bottom of the pecking order kind of bought into it. They might complain about it, but they bought into it. And of course, in material science, that's all completely different. And when I talk to people at these big facilities, one of the things that they point out to that they like is that the teams are not necessarily very big at all. So whatever it is they are doing, it's not, it certainly allows for more flexibility and more individualism. But it's on the other hand, there's a great deal of incoherence.
Raise your hand, John.
On the other hand, when you talk about big science, in an environment that's pretty constrained, there's another context of big science. For example, Roger Revelle, after the Operation Crossroads, first post-Hiroshima and Nagasaki nuclear tests in the Pacific, talking about how atomic bombs had turned the whole world into one big science project with radionucleotides circulating all the way around. And what I find more interesting, frankly, because I think this big science particle physics thing has been done to death, is all the other realms of big science that developed initially because of the artifacts of particle physics. And in particular, Ron Dole uncovered, you probably know, most people know him, wonderful historian. He uncovered a declassified secret document of the Research and Development Board of the Department of Defense that was born out of the War Department in 1947 and 1948. The Research and Development Board did a secret project about anticipating what to do next in all kinds of realms. And there was this kind of Rosetta Stone document that Ron uncovered, and I published on it as well, where they basically said there's all these realms of what we now call the earth sciences or the geosciences, and we expect there's going to be all kinds of strategic military applications that can come out of it, but the key thing is, the way we're going to get those is to do basic research in all those realms. And from what we've learned through World War II, we know that if you do basic research in the terms of the scientists themselves, that other applications will become available. And there's this little list, one-page list, the Rosetta Zone. And it starts with geodesy, my favorite, and cartography, oceanography in many realms, atmospheric sciences, seismology, etc. And they talk about let's put money into all of these domains of science and we'll get results. And they did. And they did get results. And it's this whole other world that's outside of particle physics and, you know, supercolliding, super confusing colliders. You know, it's like this two-dimensional linear thing. Things go up and then they go down. But there's all these other 3-, 4-dimensional things that are going on that are really outside of this story of high energy physics. But that's like a major...
Well, then, you know, I have two things to say to that, and that is that the big science era wasn't just about particle physics, and the new big science isn't just about material science. There are all these other projects, even at the national labs, that look at a wide variety of different subjects. And I would also say, as an aside, that one of the things that I haven't talked about is that around 1980, another thing that happens is that the defense laboratories become these self-sustaining, more or less self-sustaining entities that have a little bit of basic research but also have a lot of applied research as well. With funding that comes from the Department of Defense, with a lot of funding that comes from the Department of Defense. So it's a very complex, I certainly would agree with you that the big science era was not just about particle physics.
Before I ask my question, a comment on the last conversation. We can thank particle physicists for the World Wide Web and molecular engineers for pushing Moore's Law, and Bell Labs for efficient optical communications to allow oceanographers and geophysicists and atmospheric scientists to act like big science now, put their data together worldwide. It's turned many individual scientists into big science projects. But they have the problem you mentioned. They're not used to working together like particle physicists have. So my question to you, first of all, wonderful talk. And secondly, in your analysis of the DOE complex, and I use that word because you know it well, has there been a continuation of the Trimble piece, gentleman's agreement?
Mainly what I see is a longing for a new one, and and you know, it's a whole different world because these material science accelerators have a much longer lifetime. They're upgraded, but it's not that. You know, it's much more sustainable growth. So, I mean, the newest DOE lab that I know about is at Michigan State for nuclear physics, you know, this rare isotope machine. So, I think my own feeling is that Trimble piece was, you know, was quite a guy and came up with something that really had a long-term benefit for the national labs and material science. You know, not sure that we have many like him now.
And I think your supposition that he asked the lab directors not to complain about another project, that has generally held true.
You speak highly of Lou Ionello. I'm sure you know that he was actually selected to become the permanent director of VES by Will Happer, and Will Happer was fired, and Martha Krebs came in, and she was the one who hired Pat Damer. Do you think directions would have been, I mean, the direction of the VES or the Office of Energy Research would have been any different if Lou had remained there?
I don't know. I knew Martha Krebs, and I've heard a lot about Pat Damer, mainly, about what strong leaders they are. So I'm not sure. I think it's more, what I saw with Ionello was that he was really the right guy at the right time to put up with Shirley as the complex made this transition.
I have one quick biographical question for you, and then a more substantive one. I'm a historian of philosopher of biology, and I recently taught a course comparing the 17th century mechanical worldview with the way we use mechanisms in contemporary biology. And we used Richard Westfall's very good book about the 17th century, and you are perhaps related to him?
Sadly, no.
Oh, well, I was misinformed about that, so people hypothesize that you are. The substantive question I wanted to ask you is the contrast with the Human Genome Project and these big science labs, because that was done in a distributed way, and NIH didn't set up, one institute for all of them, to everybody to be there, to work with it, etc. So it seems like an interesting contrast with your lab, the labs, and the way it was done in the cases you're talking about. And I just wondered if you had any comment about that.
Well, one of the things that I thought of also with one of the previous comments is that at LBL, the next project after that to justify their existence after they had the advanced light source, which was kind of small once it was built, was the Human Genome Project. They supported the Human Genome Project. And after that, they got a big computer network going. So,
I'm sorry, could you say again where that was?
Lawrence Berkeley Lab.
Lawrence.
So, the largest accelerators at the largest laboratories are for material science, but that doesn't mean that there aren't other projects that are subsequently being used to justify the existence of labs. And things just got a lot more complicated after 1980. And I know Dan Kevlas and others have looked at the different kinds of big science and classifications of big science. And I really am focused on big science as an era in the national labs, not in the various kind of ways that you could organize science in a big or not so big way, although that's an interesting subject.
Okay, other questions? David, don't go too far, he's right there.
This is definitely off the top, but the idea of the basic nature of the technology, the key technology, in defining limits is one maybe to consider here. In astronomy, which is the only thing I know anything about, the era of the larger and larger aperture is right now competing with distributed aperture, which raises the Genome Project. Many institutions engaged equally in the collection of data in a coherent way. And there is now a growing concern or question in astronomy, over bigness. It started, it certainly has been starting for the last 4 or 5 years. Now, in the case, I don't know what particle physics, how it would be socially constructed to accommodate more people, and also greater, in the case of astronomy, greater resolution, greater energy, that sort of thing. In astronomy, you can do it in a distributed way. Can you do that, or is there a way that it could be done in high energy physics?
I don't know, but I'll make a tangential comment to that, that I've been in fascinating discussions with our friend Robert Smith about how the telescope community never really followed the big science pattern or the new big science pattern. That it's just a different tradition altogether. And it's his article that he sent that we're going to use as a kind of appendix or something addition to the book because it's so brilliant, that convinced me that the end of the Cold War wasn't what killed the SSC, because at the same time that the SSC dies, a telescope project, and now I'm not going to remember what the name of it, has trouble but survives. So Hubble, and then there was another one that came after Hubble.
Some ground-based telescopes.
Right.
It was a question of limits.
Right.
And in fact, the limits really started in the 70s, in their late 60s and 70s. And it got astronomers who were laboring under their decadal surveys. Astronomy was the first to develop the decadal surveys, and so were politically exposed. I mean, that was a brilliant move by Leo Goldberg in the early 60s, because it did sort of even the playing field. And we're seeing the result of that now. But now many disciplines have their decadal surveys, for better or worse. But yeah, wasn't the SSC problem the fact that once they chose the site, they lost congressional support?
Well, that was one of the problems. And
they didn't anticipate that.
Yeah, why? I mean, I look at, frankly, to be really crass at it, I look at the people who were advocating the SSC, and they just didn't seem to be as good at doing it as the people who, for example, advocated Fermilab, and it was a harder job because it was more expensive. So, and I got my ammunition or my evidence for the lack of leadership and management was from Reardon, Hodison, Cobb's book, Tunnel Visions.
Catherine, several of us in this room have our standard questions. Let me raise the one about gender, and can you just say how it fits into your story?
How does gender fit into this story? I guess what immediately comes to mind is that by the end of this period, one of the big players is Pat Damer. And somehow the other thing I can say is that when I went to the Advanced Photon Source user meeting, the gender balance was much more equal than it ever was in a particle physics or nuclear physics users meeting. So the diversity in the materials science community and the access and opportunities for women are, the diversity in fields and just the fact that it's not this old boys network means that that's one of the ways in which these facilities have greater opportunities for women and for people of color and just in general.
Any other questions? Yes. I like doing it this way.
So you talk a lot about the labs, and I think they're the biggest part of the science. What's happening in Europe, and what about CERN?
Well, at CERN, they still have a major particle physics accelerator. Particle physics is still alive on an infrastructure level in Europe. At the same time, I see signs that material science is starting to become dominant in Europe as well. Our Swedish collaborator, Thomas Kaiserfeld, is the one who's looking at developments in Europe in material science. Material science is much more international. It's not even just Europe. CERN is still dominated by particle physics, but it looks to me as though it's going to hit the wall. I mean, most of the particle physicists I know are unclear as to whether the Large Hadron Collider will be upgraded. And I guess there's Science City and something in Japan for a $20 billion next big thing. But people are uncertain as to whether it will exist. It just seems to me on a logical level that particle physics has a limit in terms of how not only how much money does it take to build, but how do you get the people to the accelerator builders and the users, and that there's a size problem with rapid expansion of growth, it seems to me.
Okay, well, thank you very much. Thank our speaker.